In this video, I'll be going over section 14 of the Fundamentals of Engineering exam, and it is titled Mechanical Design and Analysis. This covers pages 431 to 462 in the reference handbook. This section has roughly 9 to 14 questions on the FE exam. It focuses on machine design and mechanical components like springs, pressure vessels, piping, bearings, and transmissions. It's kind of unique because it also covers topics that are common in the thermal and fluid dynamics section. It involves things like hydraulics, pneumatics, and electromechanical components. This is the outline from the FE handbook of what can be covered in this section. The highlighted ones are the ones that I'm going to be going through today. I'm going to start with springs and do a few examples from there. That seemed like a little bigger section, and I think more common in the FE practice exams. And then I'm going to move on to manufacturability. This is a topic that I never really was involved in and had a lot of knowledge in. So that's kind of why I decided to cover that section. And then we're going to end with failure theories and analysis, just because it's kind of easy to get some of these mixed up. And I'm going to use one example from there. And really kind of try to break down and so you can be able to sort through them all. So as I said, we're going to be starting with springs. This screenshot here is actually from the FE reference handbook. So it kind of showed, just to give you a rough idea of what it looks like and what you can use on the exam. You have a bunch of different equations and a bunch of different diagrams, all of which are at your complete disposal to use. You have a search bar in the top of the browser that you can go through and see, and you can search certain stuff to be able to find these equations. But it is still needed to have general knowledge of which equation to use, and that's kind of the most important part about this exam. So going over springs a little bit, it obviously, as you can see, the shear stress equation's right there. That's kind of your main equation when you're working with springs. That's the one you're taught. And then obviously you have F equals Kx, which is the spring rate constant. And you can also find that using that equation. And then it also talks a little bit about springs in series and springs in parallel, all of which should have been covered in previous classes. But it's really good to review these parts and know where they're at in the FE handbook, because you won't be able to have the time to really sort through, especially on the little easier questions. You're better off to get those done in a timely manner, but it's also very important to get those done right, because those are easy questions that should come easy to you and definitely help your score a little bit. All right, so starting with springs, we're going to start off with an example here. I like to read the question first, obviously, and then I like to highlight the points that are given, or what rough equations from the handbook we're going to use. So reading the questions here, it says a helical compression spring. So we know it's a helical. Has a wire diameter of 2.34 millimeters, and outside diameter of 15 millimeters. For a spring load of 150 newtons, the shear stress in megapascals in the spring is most nearly, and gives 4 options. Now there's a lot of questions like this that it's not going to be an exact answer. It's going to be, you're going to do the math and stuff and say you're going to get 340. So you really have to know that going into the test. That's something that's very, very important. So let's start this off. I know we're going to be looking for shear stress. That's what we're trying to find. So if we go back to the last slide, we can see that the equation that we're going to use is right here. Now, if you didn't know that, you can use that search bar and you can go in and type in shear stress, and it should take you roughly to this page. You might have to go through some, but you know you're looking in the spring section. All right, so now that we know what we're looking for, we're going to identify some of our variables. So we know that D is 2.34, which is the wire diameter, millimeters, and that we know the outside diameter is 15 millimeters. So we're going to call that DO equals 15 millimeters. Now, if you look at this equation from the last slide, shear stress is equal to Ks 8FD over pi d cubed. So obviously we have a couple variables here that don't come easy. It's not like you can just plug them in and play. So again, going back to that slide, you can see that you can find in the handbook that this big D here is actually D outer minus wire diameter. So if you do that equation, that's going to give us 15 minus 2.34. And if you do the math there, that'll equal out to 12.66 millimeters. Now, D is basically your mean spring diameter. So we're just trying to find that distance there because we're going to need that in the equation for shear stress. And again, looking at the reference handbook, you're going to find this equation right here for C equals big D over little d. And the reason we need C is this Ks term right here. The equation to this term is 2C plus 1 over 2C from the handbook. So it's crucial that we get C here, which again, I mean, you're kind of just plugging in values. We know the big D is 12.66 divided by your wire diameter, which is 2.34. If you do the math there, that'll give you 5.41. And this is basically just the ratio of the outer diameter to the wire diameter. And again, this comes into play right here when we find the value for Ks, which I said a little bit ago, equals 2C plus 1 over C, 2C. Again, just plugging and playing. 2 times 5.410 plus 1 over 2 times 5.410. And this will give us a Ks value of 1.0924. So if you're looking at the equation in the upper right, we have our Ks value. We have our force value, which is your spring load of 150 newtons. And we have our D, which is our wire diameter. So we have all the variables. So now it just comes down to plugging it into the main equation that it gives in the reference handbook for finding the shear stress. So we're going to write this equation again. Again, I like to keep it all laid out. It takes a little bit more time, but when you really make sure and check that you have all your variables, that's the important part to not messing up an easy question like this where it's a little bit of plug and play. So we're going to go 1.0924 times 8 times 150 newtons. And again, we're looking for megapascals. The units on this problem specifically will match out, but units are another big thing it's when you're moving fast in this exam, it's really hard to skip over the smaller steps, and you're going to be sitting there trying to look at an answer, and you can't find it. And that's probably because your units, first off, unless you have the wrong equation. But finishing out this problem, just plugging in the values, 2.34 cubed, that'll give us 412.3 MPa. So again, like I said a little earlier, it's not an exact answer, but I mean, as you can tell, 412 is obviously C. So C is our answer to that one. Moving on, we're going to do another spring example. This one, again, it's going to be in the mechanical spring section of the mechanical engineering chapter of the reference FE handbook. So again, we're just gonna start from basic. We're gonna read the question, identify the variables, and try to use that to our advantage a little bit in searching for that in the FE handbook for what equation we need to use. So it says a helical compression spring has a spring constant, which is K, of 38.525 newtons per millimeter and a free length of 190 millimeters. Free length. The force N required to compress the spring to a length of 125 millimeters is most nearly blank. So the force required to displace a spring in amount X from its free length is the simple spring equation F equals Kx, where K is the spring constant or rate. In this case, our X, because we're going to compress the spring, we need to find basically it's delta X, where it's free length minus the compressed length. That'll give us at least delta X in our easy F equals Kx equation, because if this is our required force that we need and we're given the spring constant, we need to find X. Now again, this might be a problem that might trip somebody up if they're trying to move quickly through the exam. They just might plug in either the free length value or the required 125 millimeters value into X. And again, it's all about taking your time, staying calm, and making sure that you're doing these easier questions correctly. So if we get into this, delta X, so we're given a free length of 190 millimeters minus our 125 millimeters, which is our compressed length. This gives us a delta X of 65 millimeters. Now the force required to deflect the spring this amount, as I showed above, is F equals K delta X, because we're trying to compress the spring. And we, like I said earlier, we have K and we have delta X now. So we have all of our variables. So now you just plug it in, you solve it. So the required force that we need is the spring constant, which is given to us, and that is 38.525 newtons per millimeter times 65 millimeters. And again, we're looking in newtons too. Quick unit check here. We're all good. These millimeters will cancel out. If you just multiply straight across, you'll get a force value of 2,504 newtons. So again, this will be B. It's not the exact answer, but they give you just a rough range, which kind of helps you in the more detailed problems where you're working on it for a lot longer, and you know you have the right equation. It gives you a rough range of, like, this is the value. I mean, as you can see, the other four options in this question are nowhere near 2,500. They're all, the closest one's 1,000 off. So it kind of, if you get 2560, 2570, like you can basically assume that it's going to be B still to this point. Moving on to our last spring example here. This one's a little trickier. So we got the two easy ones out of the way. I just wanted to stress the importance of doing those in a timely manner, but also paying attention to the small details. In this question here, again, you can search in the search bar, and this is going to take you to the mechanical spring section in the mechanical engineering chapter of the handbook. And this is actually, reading this question, this is an interdeterminate axial load question. So you can find this section there. I did not have it in that beginning slide for the springs. So all you need to do is just go in the handbook and you search indeterminate axial load question, and you will be able to find it. So let's get started with this question. It says a screw rod is fixed at its two ends, A and C, as shown in the figure. A nut initially is in the center of the rod is supported by a spring. The spring constant, K equals 30 kilonewtons per centimeter, and is initially in a neutral position. When the nut is screwed down 2 centimeters, the support force in kilonewtons at the top of point A is most nearly what? So what we're trying to find in this question, obviously, is the spring force in kilonewtons at the top of A. So this is a little bit different of a problem than the other ones, obviously. Again, I like to start off kind of simple here and draw a free body diagram. You're given a very large piece of scratch paper and a pen that you can draw out and all these problems and work as basically as long and as much as you need on this scratch paper. And I'm one where I like to see it graphically. And whenever I can draw a free body diagram, that's kind of how I can visualize the problem best. So I'm going to do that right here. This is going to be a very rough drawing, but there's our head of our screw here. There's there and there. Now, if you look at the forces on on this problem, we're going to be looking more at this one right here. Obviously, there's a force that's pushing down to compress that screw. So we're going to draw that downward. And then there's obviously another force going down in there. So that this is an A, and it has two different components. So we're going to write FA, and this one is, we're going to call that FC. So there's that point C. Now, this spring is causing, you're tightening this nut on there, but the force is going up, right, from the spring. So we're going to show that by this right here. And we're going to say that this is our load. Okay, and just getting out some dimensions right here. So we know that that screw head is 2 centimeters, and you have your other dimensions over here. So when that spring is compressed down, your LAB, we're going to call it because B is at the center here. We're going to label where we're at. This length right here to the bottom of this screw head is going to be LAB 7 centimeters. And then obviously from here you have LBC equals 3 centimeters. So drawing a good free body diagram is kind of crucial to seeing what's going on in this problem, and really determining on the easiest way to go about it. Again, throwing it back to the reference handbook, you're going to find an equation in there for a load, an intermediate axial load. And that equation is actually P equals K times delta L, which is very similar to F equals KX. But this time, I mean, our P is our force going up. So we're gonna just plug in some values here. We know K, we know delta L, because delta L is 2 centimeters, because that is the time that is the space that it compresses down. So we're going to substitute these values in, double check our units. Centimeters times 2 centimeters. Centimeters will cancel out, and we're left with 60 kilonewtons. So that is our load. So the kind of question in this problem is, what do we do with the FA and the FC? So if you look in there more, it says the force equilibrium equation in the statics chapter. You're going to find the equation that is FA plus C, FC, FA plus FC equals P. So that tells us right away that we need to find these values of FA and FC. So to do that, we are going to kind of break it down a little bit. We're going to call this XAB, which is, we're going to use just the magnitude. And that is actually, if you look at it, XAB is equal to the magnitude of XBC. Simplifying that a little bit, and I'll show you in a second kind of where I'm getting those values at. But we're going to go FA times LAB equals FC times LBC. So basically all that's saying is FA up here will be equivalent, if you times your force up there times your length here, it's going to be equivalent to the force at the bottom times the length at the bottom. And again, you can find this equation in the statics chapter. Again, it's just another thing that you wouldn't really know. So you kind of gotta know where you're going with these problems a little bit. So the value we're going to be trying to simplify for right here is FC. And doing so, we're left with FC equals LAB over LBC times FA. So now that we have FC, we have two equations and we have two unknowns right here and right here. We know P, we know our lengths, so we have FA and FC. So we could start with this equation right here. We know that FC is equal to LAB over LBC times FA. So we're just going to plug that in for for FC. LAB over LBC times FA, and that'll equal out to FA LAC over LBC equals 60 kilonewtons. From there, I mean, it's just plug and play. Again, we have all the values. So we're just going to plug those in and it should give us an answer. 3 over 10 is LBC is 10 times 60 kilonewtons is equal to 18 kilonewtons, which is B. Moving on a little bit. So that is kind of the three main questions that I want to cover with springs. Again, you have two simple ones where you're going to find those right in the spring section of the mechanical engineering section 14 in the handbook. But this one required a little bit more. I mean, like I said, you kind of had to know and understand. That's why I like to draw a free body diagram. It really gives you a good understanding of what's acting on what. And that will really help you kind of understand where you're at and what you need to find. The FA plus FC equals P. You can find that in the statics chapter of the handbook if you did not know it already. But again, that's where it's super important to just be familiar with basic problems, because you're going to come to use those equations in multiple different questions that you might not think. So we're going to move on now to manufacturability. This is another section that it was pretty long in the FE handbook. I'm taking that as they might ask a couple questions about that on itself. And basically, manufacturability section, it assesses your understanding of manufacturing processes and their implications on things like design, cost, quality, and efficiency. It aims to evaluate your knowledge of various manufacturing methods. So as you can see, again, this is a screenshot of the FE reference handbook, but these are problems that have to do with bolts, holes, stuff like this. I just wanted to include these pictures. We're going to use some of these equations actually, and it's really nice too because it includes some definitions. So roughly, if you don't know what you're looking for and you just search it in the search bar, one of these might come up and really point you in the right direction for where you need to go to a certain type of problem. So let's try an example problem with this. We're just going to do one. Again, it's a little longer section, and these problems take a little bit more time to complete. But we're in the manufacturability section in the mechanical engineering chapter. So we're going to start out by reading the question. A steel pulley with a minimum room temperature bore diameter of 100 millimeters. So this is minimum bore diameter of 100 millimeters is to be shrunk onto a steel shaft with a maximum room temperature diameter of 100.15 millimeters. Steel shaft. And we are to assume the following here. Room temperature is 20 degrees Celsius, and the coefficient of linear expansion of steel. It's really nice that they give you that, so you don't have to go searching for that anywhere in the tables and charts in the handbook. And then the required dimensional clearance for assembly is 0.05 millimeters. So the question wants to know, to shrink the pulley onto the room temperature shaft with the desired diametral clearance, the pulley must be heated to a minimum temperature of most nearly what? So we're trying to find the minimal temperature that the pulley must be heated to get this desired diametral clearance. So again, we're going to start it off really simple here. X diameter, and if you look in the reference handbook, it's going to give you an equation, and I'll write here in a second, where we need to find X diameter. That's kind of the only thing that we don't really know. So once you find an equation like that, then you search for your values that you know or don't know. And then if you don't know them, you got to find another equation to get to them or use common knowledge. But here you go. This is X diameter equals D of shaft minus D of pulley plus required assembly clearance. So we know that the diameter of the shaft, that the maximum diameter is 100.15 millimeters minus 100 millimeters, which is your diameter of your pulley, plus the required assembly clearance, which is, as you can see here, is given to us in the problem as well. So we're going to add 0.05 millimeters. Solving for that, you are going to get 0.20 millimeters. Now again, going back a little bit earlier, how I said you're going to find this equation. You're going to find this equation in the manufacturability section. And you're also going to have to use the thermal deformation section. And that's kind of the part about section 14 that's super tricky sometimes. Like you're going to have, it involves so much. It's super broad. So you're going to have to go back to things like fluid dynamics and thermodynamics to find some of these equations that you're going to need to solve some of these problems. But again, use the search bar. That's the biggest key and point that I can recommend. It's given to you. It's super easy, and it's a lot quicker than just scrolling through all the sections. So you're actually going to find this equation I'm going to write right now in the thermal deformation section of the Mechanics of Materials chapter. Which again, just searching some of the main points of this question, you're going to be able to find it. So we're going to try to find the required temperature change of pulley diameter. So if I did not know that that was in the thermal deformation section, I could type it in the search bar. You probably have to go through a couple of different sections to get there to find the right one that you know you need. But again, this is where it comes down to understanding and laying out what variables you know, and finding the right equation for you. So the equation that you can use to solve this problem is actually X diameter equals alpha D delta T. So for this problem, we are going to try to find delta T. Solving for delta T, you get delta T equals X diameter over alpha D. Plugging in your values here, you get 0.20 over your value that you're given here, which is 11 times 10 to the negative 6 per degree Celsius, which the degrees Celsius are going to cancel out, times your D, which is 100 millimeters, which is just your minimum bore diameter, room temperature. So room temperature, it tells us, is 20 degrees. So we're just going to put 100 in there. And solving this equation, you're going to get 181.8 degrees Celsius. Now you might think, oh, well, that's the answer, right? There's a value here that is 182, like rounding up, like it's got to be right. But this is kind of where they get you. So this is just the required temperature change of the pulley diameter. It wants us to find the minimum temperature that the pulley must be heated. So again, this is one that it's a little tricky. It might take you a minute, or you might just put C, but C is actually wrong in this question. So you have to kind of break it down. So we're going to try to find T here. So we know the temperature of the room plus delta T, because that'll give us the temperature that the pulley must be heated at a minimum room temperature. So again, the minimum room temperature is 20 degrees plus our value of delta T, which is 181.8 degrees Celsius, gives a value of 202 basically 202 after rounding. So the correct answer here is actually D. And again, this is one of those problems where it's easy to mess it up. Say you again, finding the equation is another really tricky part of this question, but say you did find the right equation, this value right here is not the right answer, but they trick you by putting one that looks like it is the right answer. So that's kind of where the general knowledge comes in. You have to stay well aware of what the problem's asking for, and how you can really get it. So that's really all I wanted to cover with the manufacturability part. There's a couple more difficult questions in there about bore diameters and such. That's kind of a quick one, just to really get the idea of you might have to experiment with other sections to find some of these equations. That's where the general knowledge of understanding what the question is asking, and given the values that you know, how you can find that answer. And it tricks you up a little bit at the end. But we're going to move on now to our last section, which is failure theories. Failure theories was another one that I wasn't super confident in. Looking at the FE handbook before I take my test, I wasn't really sure of some of these. I've never heard of modified Goodman theory or the Soderberg theory. But again, it's just something to know that it's in this section. So if you search something and it says, oh, it's on page 10, like we're in section 14, so we're going to be in the 491 or the 461 to 491. We know we're in the 400s for this problem, or for these problems when we're talking about failure theories. It's not to be said that you can't find an equation in another section or whatever, but if you really want to have a really good understanding, you got to know which topics are covered in each section, because that'll help you find your equations a lot faster. So we're going to do an example here real quick. This is not from the FE practice exam. The other examples that I did were. This is one that I kind of used from another class, super important. But basically the failure theories section, it assesses your understanding of the principles and concepts related to the prediction of material failure under various loading conditions. And a lot of the time it covers different failure theories used in engineering to predict the failure of metals and materials and structures. And like I said before, some of the key topics of this section are stress analysis, failure criteria, brittle and ductile materials behavior, and you're going to have to do a factor of safety. So looking over this question real quick, it's telling us a machine component is subjected to silicic loading with a mean stress of 20 megapascals and an alternating stress of 30 megapascals. The yield strength of the material is 300 megapascals. In tension, that's important, and 200 megapascals in compression. Using the modified Goodman theory, determine if the component is expected to fail under the given loading conditions. So obviously it gave us yield strength. Those are all loading conditions. Those are conditions where it wants you to be in there. And if you go back to this slide, Again, this is a screen clip right from the FE reference handbook. So just looking at some of these variables, I know that I have some of these values in here, right? I have my alternating stress, I have my endurance limit, I have my mean stress, and I have my yield strength. So I know that this is the equation that I want to use. And the question even said that to use the modified Goodman theory. But if I did not know where, if you know the variables of mean stress and such, like the sigma is the Greek letter for stress. You can probably find the equations that way. So going back to it, again, we're just going to write the equation that we know we're going to have to use from the previous slide. And that one is mean stress is equal to your alternating stress over your endurance limit plus your required mean stress over your yield strength. So just looking at the question again, I like to identify your variables, and some of these can get super wordy, so I like to write them out just so I don't mess them up, and it's kind of easy to mess them up sometimes. This question isn't super difficult as long as you know what these variables are and what they mean. So it obviously tells you your alternating stress up here of 60 megapascals, or 30, sorry. See how easy that was for me to mess up? And we also know that our target mean stress is 20 megapascals. And our endurance limit, this is an equation that you should probably know it off the top of your head if you took a statics class or any analysis classes. It's actually 0.5 SY, which SY is your yield strength. Now, looking at this equation, again, you plug in your endurance limit, and you're left with all the variables of this problem. So you just have to find the equation. So we're going to do a little substitution in here. 30 megapascals divided by, we know that SE is 0.5 SY. And we know that our SY, which is our yield strength, is 300 megapascals. So we're going to plug that into the bottom of our equation here. Plus 20 PAs over 300 megapascals. Now, after simplifying this equation a little bit, we get 30 over 150 plus 20 over 300 is similar to 0.2 plus 0.0667. So solving for this here, you get your mean stress to be 0.2667 MPa. Now this problem, because I had to find it in a previous class, it doesn't have any answer choices. But obviously this question doesn't want an exact answer, like a number, because it says determine if the component is expected to fail under the given loading condition. So we need to figure out whether it's going to fail or not. And to know that or not, again, we can look back at our FE handbook, and this says that the modified Goodman criterion states that a fatigue failure will occur whenever. So this is telling us that a fatigue failure will occur. This is huge right here. That's if the mean stress is greater than or equal to 0 without a factor of safety, and our mean stress is greater than or equal to 0 with a factor of safety. And you have these values over here too that you cannot forget, which is 1 over n. So it's got to be greater than 1 over n. So we don't know an n value. So we're going to use this top equation here in solving this problem to see if ours aligns in here. But again, the main part about this is this is telling us fatigue failure will occur. So we need to find if the component is expected to fail under the given loading conditions. So obviously looking at our answer here, we know that our mean stress is 0.2667 megapascals. And this value is less than 1. So the component is expected to withstand the given loading conditions. Without failure, according to the modified Goodman theory. And again, this wasn't a multiple choice questions, but they're not all multiple choice on the FE exam. You're going to have some fill in the blanks. Those are usually more numerical values. But even if a problem like this were to appear and ask for the mean stress, then you have the equations, you have the variables, you just got to plug it all in, and you're good to go. So to leave you off, I want to give you some tips for this section. And I kind of went over, I'm sure I said these throughout the presentation, but they're super, super important in getting these problems right, and understanding where everything's coming from, and hopefully passing your FE exam. So the tips I have for you are understand and become familiar with the exam format. Like I said, their answers are not going to be exact, and that's kind of the thing that catches you off guard a little bit. You're like, oh, well, it could be that one, but it's not the exact answer, because, I mean, all through our college lives, we're trying to find the exact answer. So it's understanding that and really preparing for the exam format, and that's where those FE practice exams come in very crucial, because it gives you a big layout of exactly, not the exact questions, but exactly how certain questions are going to be asked, how the answers are presented. All of that, understanding that and becoming familiar with that will only help your score in the end, because you don't even have to think. You're like, okay, if I get 254 and there's an answer that says 250 and the next question or the next closest one is 300, then I know it's a 251. So it's just super important to understand that. But I would definitely review basic fundamentals of each section. Again, going back to having to find some of the information in some of the other sections. Sometimes you're going to have to know this is, okay, I'm going to have to use a statics equation, so let me get to the statics section of the handbook. And then another tip I have is practice problem solving with different types of problems. Like I said, even that last problem, that's not on any of the practice examiners or anything, but it's just nice to be able to review that and know that you can use some of those equations in the handbook for questions that you might have never seen before or might not know what to do with. It's just super important in practice. And then that leads me to familiarize yourself with the provided handbook. You got to know where your sections are, what section roughly the question's answer is in. All that stuff is super important. I mean, this is a timed exam where you got to kind of get it done. You got to get the easy problems done quickly and efficiently and properly, and then spend your time on the little longer questions that you require super long equations, stuff like that. I mean, the more time that you can save on those easier problems, it's only going to help you in the end. I've had other classmates tell me that they were running out of time, so they just started guessing. I mean, I did not get to that point, so it's more or less the fact that you gotta be weary of your time, so you familiarize yourself with where you need to go in the handbook, because that'll be your safeguard right there. And then the last two pieces of recommendation that I can give you is stay calm and stay positive. And that's kind of the biggest thing I heard from other people that have passed it going into this exam is, oh, it wasn't that bad. It wasn't as bad as I thought it was going to be. You have to have confidence in yourself, and you have to stay positive even when you come across a question where you might not know what to do with it. It's super important to just stay relaxed and stay positive. I mean, you got 110 questions. You don't have to get all flustered over one. But with that, I wish whoever takes this video and uses it the best of luck. You got this and you can do it. It's definitely possible.